So we could evaluate this limit simply by plugging in the 2 for the x. And that's going to give us 5, which is exactly what we got graphically, what we'd expect. So now we want to use this definition to prove that this is true. So the easiest way to do that is to start at the end and work backwards. And this sounds a little confusing. The way I like to think about it is that f of x minus L is going to be less than epsilon whenever x minus a is less than delta. So this will be true whenever this is true. So in this case, we want to start with this piece, how the epsilon is defined. So we're going to start, it's going to be our absolute value of f of x, in this case is going to be x plus 3, minus L, our limit, 5. So our goal now is to somehow manipulate this so that we could find this in it, x minus a, the absolute value of x minus a. In this case, our x is x, and our a is 2. So we want to manipulate this somehow to get it to look like x minus 2. Which, we're in luck. If we combine like terms here, it's going to give us absolute value of x minus 2. Great. So if we go back to our definition here, we know that this is less than epsilon. So we just say that this is less than epsilon. But if we go to the definition, this is also less than our delta. So that means we could choose our delta to be equal to our epsilon. So that means our delta equals our epsilon. Okay, so now if we want to analytically prove that this relationship is true, we've already decided on our delta. And how is our delta defined? This is the difference between x and a is less than delta. In this case, x minus a is going to be x minus 2. So we're going to have x minus 2 is less than delta. But we chose delta to be our epsilon. So that means x minus 2 equals our epsilon. So we know that x minus 2 is less than epsilon. And we could rewrite negative 2 as positive 3 minus 5. So if we decide to do that, we have x plus 3 minus 5 is less than epsilon. And that is this piece right here, our f of x minus L is less than epsilon.